guys, so today we're going to build on what we did last week. We're still going to look at exponential growth and decay, but specifically over the next 2 days we're going to look at some applications of it. So today we're going to look at some common situations involving growth and decay. We're also going to get into the idea of compounded interest. For those of you guys who did that extension last week on Friday, that's really going to lead into a lot of what we're doing today with the financial side of it. Then the rest of this week, we're going to spend looking at regression, which we've done a couple times throughout this year, but we're going to look at regression with exponential models as well. All right, so starting with this first one, all right, those two equations, those are the same equations we worked with last week. 1 plus r to the t is showing growth, 1 minus r to the t is showing decay. Now, these are specifically models for yearly growth and decay rates. Once we start talking about a continuous growth or decay, you may see that in pre-cal, you would use a base of E, so your equation will look slightly different. But for what we're doing in here, we're typically going to look at yearly growth or decay rates. All right, so looking at this first one, it says the value of a car in thousands of dollars can be approximated by the model given. It says T is the number of years since the car was new. So the first thing we determine is whether or not this is showing growth or decay. Well, let's look at our base. Our base is less than 1, so this is showing decay. The next thing wants to know, what is the annual percent increase or decrease? Well, it's decay, so it's going to be decrease. So that percentage, remember, it's the R in the 1 minus R equation. So this is not a 92% decrease. That would not be a car worth buying if that was the case. Remember, 1 minus R is equal to 0.92. So negative R is equal to a negative 0.08. Your R is 0.08. So if R is 0.08, then that means that that percent is 8%. So this is an 8% decrease. Then what we need to do is estimate when the value of the car will be $9,600. So this is today and next class are very heavy calculator days. So if you do not have a calculator with you, remember you can access the Casio on the iPad. There's directions on Schoology for you to do that. You also can use some other tools that are online, something like a Desmos if you want to use that as well. But using that Casio emulator may help you just be more comfortable with this when you come back to school next year and you're actually using the Casios. All right, so if we want to estimate when the value of the car will be $9,600, we need to consider if 9,600 is going to be an X or a Y. Well, the X or the T stands for time. This is a dollar amount, so we're looking for the time. Now, the other thing we need to consider, if I set this up where I do Y equals 31 times 0.92 to the T, in order to find an X when I'm given the Y, there's two different things you can do. So one thing you can do is you can graph it, you can do G-solve, and then you can do your XCal. XCal will give you a Y equals option, you'll plug in what Y is, and then you'll see what the corresponding X is. A lot of people actually miss this one though, because when they do this, they're going to say that Y equals 9,600. So while we want to know when the car is 9,600, we need to look at the equation that we're given. The equation that we're given has an initial value of 31. Well, that car didn't initially cost $31. That car initially cost $31,000 because it tells you the value of the car in thousands of dollars. So $9,600 in thousands of dollars is 9.6. So the Y value that we're going to use is 9.6. So what we're going to do is we're going to graph this, and then we're going to do XCal, and then we're going to let Y equal 9.6. The other option you can do, and those of you guys who are using a TI-84, this is also how you'll need to solve this. We're going to graph our original equation as our Y1, and then in Y2, we're going to graph the 9.6, and then we're going to find the intersection. So you can also use that method on the Casio. I do like that method on the Casio because it lets you see it a lot more visually. That method's also really helpful for when you get more than one solution. So if you remember back when we did those quadratic word problems with like the projectile motion, or another good situation would be next year when you guys get to pre-cal and you get to your sign models, then you could have more than one solution. So it's good to see it visually. But either of these options will work, but let's go ahead and grab our calculator and graph this. All right, so I have my equation plugged in. So after I do this, what I'm going to go ahead and do is I'm going to go ahead and get a good window just to make sure I can see this picture a little bit more clearly. So I'm going to go to Shift and F3 to look at my window. So let's remember what X is standing for. X is standing for our number of years. So I'm going to keep X min as 0. I'm going to have my X max, let's just go with 20, just to make sure I can see enough of this. Y stands for the value of the car. So we don't care if the car is a negative value. Y max is our maximum value. Well, the car started at $31,000, and we're looking at this in terms of thousands of dollars, so that max is not going to be above 31. So then we're going to go ahead and graph it, and there's my picture. All right, so again, to evaluate this using GSolve, I'll go to F5 for GSolve. I'll do F6 to see some more options. And then again, I know what my Y value is. I'm looking for the X. So since I'm looking for X, I'm going to use XCal. So now it tells me to enter Y value. That is 9.6. So that tells me after 14 years, this will have a value of $9.6 thousand, which is $9,600. Again, option 2, I can go to Y2. I can plug in 9.6. I can graph it. I can GSolve and find the intersection. And I still get the same answer. I still get 14 years. All right, so let's look at another example. So this time we're going to write the equation. So it says in 2000, the population of a city was about 1.04 million. During the next 14 years, the population increased by 2.05% each year. So we're talking about a yearly growth. So to write that model, we're going to use the y equals a 1 plus r to the t formula. So a is the initial amount. We're writing this in millions, so I don't have to put 1,040,000 and have a gigantic number. I can just use 1.04. And just remember, all of your y values will be in terms of millions. This is showing growth, so it's going to be 1 plus the rate. And remember, we have to write the percentage as a rate. So I can't do 1 plus 2.05. 2.05% as a rate is 0.025. So 1 plus 0.0205 to the t. Or you could write that as 1.0205 to the x either way. So that's our model. So part B, estimate the city's population in 2008. So that tells us what x is. That tells us the time. So 2008 is not the x value though, because again, this is based off of 2000. Each year past 2000 is how it's growing. So your x value here is going to be 8. Again, you can do this one of two ways. You can graph this equation, and then you could do YCal, and plug in x equals 8. You also could just plug this into run matrix, and you can just type in your equation into run matrix and see what you get as a value. What you do not want to do is graph this, because that's not an equation. It doesn't have any x's in it. It's just going to give you a horizontal line. Now, the value of that horizontal line will be your answer, but a lot of people get confused when they plug that into y equals. So if you're plugging an equation into y equals, just make sure you have an x in there. All right, and then the second one, it says to estimate the year that the city's population was 1.3 million. So 1.3 million is the y value. So in order to solve for the x value, again, I can do the same thing I did in the last question. I can do y1 and y2 and find the intersection, or I could plug in my original equation into y1. I can plug this into y2 and find the intersection, or I could just plug this into y1, and then I can do xcal and let y equal 1.3. So either method will work. So go ahead, pause the video real quick and try and enter both of those in on your calculator. All right, so if you did x equals 8, whichever way you did it, you should end up with 1.22 million people. For part C, if you're trying to evaluate this one, you're going to end up with an x value of 11, which means 11 years after the starting point, which was 2000, which would be the year 2011. All right, now let's look at our next one. This one's a little bit different. So it says the amount in grams of a radioactive isotope after T days is given by the following equation. So, and then it tells you that A is the initial amount in grams. So it wants to know what percent of that element decays each day. So we're going to do some more stuff with half-life a little bit later on in this unit, but you guys may have seen this some in chemistry, so you kind of understand a little bit of how this works. There's actually two different ways you could solve this. One method you could use is to try to write this in the same form that we've been using, and this is going to use exactly the method we did last week. So I'm going to rewrite this as 0.5 to the 1 over 13 to the t. Then at this point I would need a calculator. I would actually plug in 0.5 to the 1 over 13 in order to figure out what that equivalent decimal is. If I do that, I'm going to get 0.9481 to the t, which I could then rewrite as 1 minus 0.0519 to the t. Then you can see that percent decay, all right, is decay that's minus, which that's the rate, move it over two places, 5.19%. The other option that you could do to solve this is you could actually think, hey, if I had let's say I started with 1 gram, and I want to see how much is left after 1 day, well, let's just plug in 1 there and see what happens. All right, so if I do that, I'm going to get a very similar looking answer. I'm going to get that y is equal to 0.9481. That means that I would have 0.9481 grams left after 1 day. Well, if there's 0.9481 grams left, that means that 94.81% is left, which means that 5.2 or 5.19% is the amount that has decayed. And you still end up with that same answer. All right, so now we're going to transition to a different type of exponential. Okay, sorry about that. So we are going to transition, like I said, into looking at some applications with money. In order to do that, we're going to talk about interest and interest compounding. So some of this may actually look familiar. You may have seen some of this in an earlier math class, maybe in Algebra 1 or in middle school math. But we're going to talk first about what compound interest actually is before we talk about the equation. So let's say you have $100 and you're going to get 10% interest on it. Now that probably is not going to happen. That's one of the things I always thought was funny. I learned these applications back when I was in high school, and then I saw in the real world I'm getting like 0.04% interest, but that's okay. But let's say it just makes it a little bit easier to see. So if you have $100 and you get 10% interest yearly, so year one, you start with $100. You would get 10% interest, which would give you at the end of the year $110. Well, in year two, you would have $110, and that really looks like a 110. There we go. Did it again. Okay. Then that year, you would get 10% interest on that, which would be $11. So at the end of that year, you would have $121. Well, when you start year three, you would have $121. Well, now your 10% interest is $12.10. So at the end of that year, you're going to have $133.10. So as you can see, kind of the longer this goes, the more you're getting interest on that interest. Well, compound interest basically takes that interest and adds it back into your account earlier so that you're getting interest on your interest sooner and more frequently. So in general, the more frequently your interest is compounded, the more interest you're going to get. Now, this also works the opposite way. Let's say you're paying interest on something like a credit card. The more often it's compounded, the more interest you're going to need to pay. So let's say interest was compounded quarterly. Well, let's look at the first quarter. Let's say the same thing. You start with $100. At the end of the first quarter, you're going to get a quarter of that interest. Well, 10% was $10. So a quarter of that would be $2.50. So at the end of quarter one, I would have $102.05. All right, let's go to quarter two. At the start of the quarter, I have $102.50. I would get 10% of that divided by 4. So 10% of that, and then a quarter of that. Well, then that's going to give me $105.06. All right, quarter three. I start with the 105.6. I get a quarter of the 10% interest, so $10.51 divided by 4. which is going to be $107.69. Quarter 4, I start the same way. I add that 10% interest. I take a fourth of it because it's a quarter, and that would give me $110.38. Well, the end of the fourth quarter of the year is the end of year 1. So now I can compare that to what I would have had if the interest wasn't compounded. So you get a whole extra 38 cents. Now I know that doesn't seem like a lot, but let's say instead of $100, you had $100,000. Okay, you can start to see a little bit more of an impact, especially if this carries over across years and years and years with a high interest rate. So the more frequently your interest is compounded, the more money you're going to have. So for compound interest, this is one of the formulas that we're going to look at. P is the principal, which is the starting amount. R is the rate. We always write the rate as a decimal. That rate is also going to be given as an annual interest rate. It's the percent interest you would get for a year. That does not affect our compounding numbers. It's just always going to be called an APR, okay, your annual interest rate. T is the time, and it has to be in years because that's a yearly interest rate. We do need to keep our time in years. So if you want to find the amount of money after 18 months, you need to use 1.5 years. And then N is the number of times that money is compounded in 1 year. All right, in 1 year. So if you're compounding it for 5 years, you don't need to worry about multiplying it by 5. That 5 is accounted for by that T value that's right there. So if your money was compounded daily, N would be 365. If your money was compounded monthly, N would be 12. If it was compounded quarterly, N would be 4. And you can keep going in that direction. All right, so let's look at an example. So you're deciding between two accounts. One pays 1.65% annual interest compounded daily. The other pays 1.68% annual interest compounded quarterly. So we want to know which one is going to have more after 5 years. So let's set up these two equations. All right, so equation number 1, I would do A. All of these are going to be A equals P, 1 plus R over N to the NT. So as option number 1, $10,000 is the principal. My rate for the first one is 0.0165 because, again, we have to write it as a decimal. That's going to be compounded daily. So that's going to be 365 for my N. And then I'm using 5 years. Option number 2, still starting with $10,000. Still going to be the same equation, different interest rate, 0.0168 divided by a different N. Compounded quarterly is 4 times a year. And then I'm just going to evaluate these with a calculator, plug them in, see what I get, and see the difference between them. So if I plug in that first equation, then I'm going to end up with $10,859.97. And then if I plug it into that plug in those numbers from that second equation, then that's going to give me $10,874.38. So even though the second account was compounded less frequently, that higher interest rate made a bigger difference. So again, anytime you're making a financial decision, you got to consider the whole picture. You got to look at interest rate, you got to look at compounding. There's a lot of different pictures for you guys to look at. All right, so the last one that we're going to look at is a different type of compound interest. So every other compounding situation, no matter what it says, it's compounded. Unless you see the word continuous, you are going to use the formula we just used. But if you specifically see the word continuously compounded, you're going to use a different formula. And this is frequently known as the PERT formula because it looks like it says the word PERT. So continuously compounded is a specific type of compound interest. Again, if you want to see a little bit more detail on this, that extension from last week Friday really goes into this. But this talks a lot about E. Now, if you remember E, when we were evaluating it, we were looking at 1 plus 1 over x to the x, and that's kind of the number. We kept plugging in larger and larger numbers to estimate the value of E. That looks pretty similar to your compound interest formula, doesn't it? So if interest is compounding continuously, that basically just means it's not compounded every day, it's not compounded every hour or minute or second, it's compounded as frequently as it could possibly be compounded. Now you'd think that's going to be a whole lot of money. Now it is going to be more than the other versions, but it's not going to be a crazy amount more. Because as those intervals keep getting smaller and smaller and smaller, if we're talking about 0.000001 of a cent, that's not going to affect your total. So eventually, I mean, it is going to kind of have that limit on it, but it is going to compound more frequently and give you more money if it has the same interest rate. It's just not going to give you an infinite crazy amount of money. All right, so again, this is the formula we'll use if your problem specifically says that it's compounded continuously. So let's look at this one. You have $5,000 to invest in an account that earns 1.75% annual interest, compounded continuously. So that is our clue that we're going to use the PERT formula. All right, it wants to know, question 1, how much money will you have in 10 years? So let's plug in our values. So 5,000 is P, E is the base E, R is 0.0175, T is going to be 10 years. So I can just plug this straight into Run Matrix, and I can look at the value that I get, which is $5,956.23. All right, question 2, when will you have 7,000 in the account? So this time, I don't know X. So this is going to be 7,000. Then that's my P. E is E. Again, E is the Euler's number E, the 2.7. R is still 0.0175, but now I don't know X. I want to know, I don't know why I put 7,000 there. I'm sorry, guys. 5,000. This is 7,000. There we go. So I want to know when Y is 7,000 when I'm starting with that $5,000 initial amount. So again, in order to solve this, we're going to talk about how to do this algebraically once we get to logs. But for now, we're going to plug this in on our calculator. Again, 2 options. Plug in your equation, GSolve, XCal, let Y equal 7,000. Option 2, Y1, make your Y2 7,000. And then either way, you're going to end up, and then intersect. And either way, you're going to end up with the next coordinate of 19.23 years. All right, so that is it for your applications. So your to-do list for today, very similar to last week's first lesson. So instead of those practice problems are going to be optional again. And the key is on there for you guys to check your answers. But the quizzes is going to be the practice grade in addition to this ed puzzle. So make sure you do that quizzes. It's pretty short again. It's got about 9 questions, multiple choice. If you need help on the practice problems, again, you can email me, fill out the video request, or do the Zoom tutoring session. And then you've got that week 4 assessment by Friday, and that will have a little bit of what we do on Thursday.